Thanks for joining. My name is Zamani. It's my pleasure to have Professor Eduard Dragut from Temple University here with us. Eduard has graduated from University of Illinois in Chicago, and he has worked on various aspects of information for natural language processing, data management, mostly interested in building scalable systems on integrating and extracting knowledge from larger scale heterogeneous corpora. He has also done some very interesting projects related to social good, for example, climate change, and also should look it up because I keep forgetting that. Assistive technologies such as augmentative and alternative communication, which I have no idea what that is, and AI-driven tools for knowledge discovery. I'm really looking forward to learn from Eduard about what his for us today. So without further ado, please welcome Eduard to UMass.
Thank you for the warm welcoming here. I had a great time so far listening to the projects, listening to your introductory projects. So now is my turn to share some of my work. So for this visit, I prepare work based on something that I thought that is quite related to the information retrieval that you do here. A bit different, but I felt that is, at least we'll see whether that's interesting to everybody. So I'm not going to talk about neural approaches for resource selection distributed search. So, okay. So what is distributed search? So a little bit of refresher. This used to be a hot topic early on, and I'm going to give you a sort of a historical reference to the topic. But in distributed search, we assume that the data of interest is not in one place. We assume that we have multiple databases or data collections, each with its own search engine and its own indexes. Then our goal, we have a broker that will need to figure out, given a query, which one of these databases to query online, right? So this is, so first what we do offline is we learn about these databases, data set collections. We call that resource representation, and I'm going to give more details about that shortly. Then we use these representations of each source at query time to decide which subset of these data collections should we call. We cannot afford to call all of them. We assume hundreds of them. Once we do that, of course, we submit the query. This becomes a distributed environment. Each of these data collections has its own search engine. We don't know how they implement their search. It's a black box. We assume that they do it in a genuine way. Then they return the list of results, of course, ranked. So our next step is that of integrating that or merging, right? And we have to remember we have now ranked list. So we have to come up with a merged list that keeps track of all the hints that we get from all these individual top K list to come up with a merged list. So this is a topic that had quite a bit of interest in the 90s and early 2000s. And besides the resource representation, resource selection, merging that I mentioned earlier, there are a few other problems of interest, one of which is vocabulary misalignment between the sources. You can imagine that we have, for instance, nowadays you can have a database that is all about social content like Twitter or Reddit, whereas another one can be about literature, on scientific literature, right? Nowadays, we have people sharing their work and discuss their work on Twitter or LinkedIn, so the merge of the two will be of interest. Of course, from a system perspective, efficiency and scalability is another problem. But in this talk, I'm going to focus on the two problems at the top. And let me give a little bit of a refresher on the topic. So let's start by acknowledging some early work, pioneering work on this topic, which goes back to 1995 or 1990s. With one of the first work was based on query-based sampling, trying to get an understanding of the kind of documents each of these databases have. So we start with seed set of queries, then we retrieve the documents, and then we learn from the distribution of the terms within documents across documents, right? And then we issue another set of queries, get another set of documents, and repeat that until some stopping criteria. Of course, you cannot afford to do that forever and ever because perhaps you are familiar with politeness and other issues related to crawling a retrieval from these engines. Once you have, we collect enough documents, a sample of documents from each of these sources, the next step is to create the representation. One of the classic algorithms in this space was by Callahan in the 1995, Corey, which was based on a Bayesian inference network. And then later on, this work was picked up by, of course, I'm only giving you points of reference. There is a lot of work there, so I cannot possibly mention everyone. So I know this will be recorded and posted online, so people who are not referenced here, apologies. I'm trying to pick and choose, but there is no, I'm not trying to pick any battles with the community by any means. So one of the works that became a bit of a seminal work was RAD-D, let's call it that way, Relevant Document Distribution Estimation by Lucy and Jamie Callahan in 2003. And I'm going to use that to kind of give you an idea of the kind of algorithms predated the neural networks. And then we'll go from there to present what we did in our research. So, so let's look at this work for a little bit to get a perspective into this area of work. So their main take on the problem was how can we look at each of these data collections from a perspective that elevates above the term distribution. So what their idea was, how about we actually estimate the number of relevant documents to a query. Right? So if we know that, then we can come up with a scoring scheme that, given 100 or more such data collections, we assign to each of them a score based on this idea of number of relevant documents. And we use that to rank them for unseen queries, and then pick a subset of them. We usually submit to less than 10 out of more than 100. As I said, this is due to multiple reasons, including politeness, but also the more you get, the more data you get, you have to spend time to merge it, right? So there are multiple aspects related to efficiency as well. So one important concept that they implemented was a so-called central sample index, where they retrieve these documents in response to these queries. They index locally, but they also kept a lineage between the query, the document, and the data source from which they retrieve that document. And we'll see why is that important, why that is important. So that is important because we make a few assumptions by this approach. One is that knowing the sample documents that we retrieve with the very based sampling, that whatever we get gives us a sense of the amount of documents relevant to the query in that particular resource. So we can use that to estimate the probability of a document that is relevant according to the source itself, given that locally you only have a sample, right? Second, that documents, whatever we retrieve from a source, is only a representative of a larger number of documents that potentially are relevant. So imagine like I have a class, right? So rather than get an entire class, you get a representative. So that document, whatever document we retrieve with our queries and we put in our local index, acts as a representative of the entire class. So because of that, now we are able to use our local sample to get an idea of the scale between what we have and what that the original database may have. So how does this work at query time in order to, so remember, perhaps I should mention this. So our goal here is not to rank the documents, is to rank the databases or the search engines, right? We have multiple of them and we rank them. So we take only the top 10 or so of them to which we send the query, right? Yes, I hope that's I want you to clarify that. So at query time, what happens, before we submit the query to the individual resources, we use our local sample index. We send the query there. We treat that as our own mini search engine. Whatever the documents we retrieve, we rank them. Then for each document, we look, where did you come from? Right? We go, oh, you went to this resource 1, you came from resource 2, you came from resource 1 again, and so on and so forth. And we also keep only the top K, whatever a K is, can be 100. So these are all documents. Can be 100, can be 220. And then we count how many documents from each source we have. And then we multiply that with the scaling factor, which is that of the size of the resource over our collection. And we use that to give us a score about the source itself relative to a new query. So, and then we rank them, and then we submit the query. So this was, as I said, one of the solutions. There are multiple other that were proposed over time, including one from Bruce in 2000. There is another solution that improve on the original algorithm that besides looking, as we did before, at the documents, they also take in consideration the rank, right? So the higher you are in the rank, I'll give you an additional coefficient to that source probably has more relevant document than the other. Around 2000, 2011, Lucy and his students, Purdue, came up with additional algorithms in this space. At any rate, with the we have the invention of neural networks, right? They bloom. We have neural IR. So in our group, we thought, how about distributed neural IR? Can we use that for our purposes? So we did that, and along with other people. So this other third paper, SLMs, is not ours. Is a paper in CIIR last year, who uses LLM for the same problem. Right? I would like to acknowledge that. The other two are our work, and I'm going to present them here. Okay? So let me give you a concrete example why neural IR is meaningful, and it makes a difference in this space. So assume that these are two examples where we have 3 data collections. I give these names so that we kind of give a sense of what these documents, the kind of documents these databases may have. So imagine they are not necessarily disjoint, but they have overlapping, but different documents altogether. So the first one, imagine, is research papers related to database indexing concrete techniques, B-trees, LSM trees, and so many other things. The other one is a database or data set collection of tutorials. And the last one is on retrieved from forums. Okay? And our query is, I want to find database indexing techniques. So now you send that query to these three, and you try to see which ones should play more. Should I trust more to return to me relevant documents? So if we only look at the terms alone, we use the classic TF-IDF, and James earlier mentioned BM25. So if you use that approach, then we get this ranking, right? Collection 2, because you can see there is quite a bit of overlap between the documents and the query. Intuitively, that will be ranked ahead of collection 1, and collection 3, we all agree that is the least relevant. But from a neural perspective, right, when you look at the semantic embeddings of the terms, even the phrases, we are able to infer that collection 1 is actually a lot more relevant than collection 2, because those are concrete instances of the indices in database literature. So here is the rest of my agenda relative to neural resources for distributed search. I want to pause here a bit. In the literature, we also find federated search. It's pretty much the same idea. Distributed information retrieval or federated search are two different names for the same topic. So the key questions here, when you move from traditional representation, for which I gave an example earlier, to neural IR, how should we represent the sources? That's the first one. The second one is, do these sources have any relationship between them? Past literature assume that they are disjoint, right? But you can see from my previous example, there is some overlap, right? So can we benefit from that overlap? And I'm going to present two directions on this. One that builds on the idea that there is a connection between these resources, and we use the graph neural networks on a graph that we create over the resources. And the other one, the other paper, the other work is we start from the question, is a vector good enough or the right representation for an entire collection? We are used to use a vector for a word, for a document, but when you go to the scale of a database of documents, is that still a good enough representation? Maybe vector is not. So then we propose box representation or box embeddings. So let me start with the first work on this topic, where we use graph neural networks to improve on the ranking of the resources. So this is the problem definition. I promise I have formulas, but I'm trying to skip them as much as possible. But we can talk about them. Please feel free to interrupt me and ask questions at the end if any of these formulas that I skip may trigger some ambiguity. So as I said, formally, we have a set of resources or databases or data collections, whatever helps your intuition to frame the problem. And our goal is, given a query, to assign a relevance to that resource for my query. And we want the relevance to be such that it allows us to rank the resources with respect to that query. So from a learning perspective, because we want to frame this problem as a learning to rank, we want to come up with a function. We denoted that G, right? That given the resource and our query, of course, with some hyperparameters, we are able to predict the relevance score of a resource. Right? And perhaps the learning functions intuitive. All we do, we have a set of label data, and we sum over them. We try to minimize the difference between the predicted value and the one that we have manually labeled. So let's see why the graph version or abstraction is intuitive. So I have, this is another example. So we start for the example from the databases. Let's now look at the example from the machine learning and IR. So the query will be deep neural networks, and we have 5 resources. Again, use the names that I assigned there to kind of give you a sense of the kind of documents will be in that resource. Imagine there are thousands of documents about deep learning in R2. There are thousands of documents in R5 related to information retrieval. Okay, so the name, I'm using the name to kind of help you anchor the kind of documents are there. Okay? And these of these have hundreds, thousands of documents each. Okay? So now, if I, with the classic representation, if of resources and trying to find the resource that better matches the query and will return relevant documents, will be resource R, right? Now, if we assume a graph representation, right, and we'll talk about how to get that similarity between resources, then perhaps that the fact that we know that R3 is relevant to our query, that will signal, that will propagate to the network. Now we have to decide how many hops. Usually 2 hops is good enough. So that we also infer that R2 and R1 are relevant, right? In the previous approach, R2 and R1 are not as highly ranked, but now because they graph neural networks, and I'm going to talk about that soon, we assume that these signals propagate according to the training scheme that we implement. All right. Questions so far? Right. So let's see step by step what we do here. First, we need to have a common representation in the same embedded space for the query and the resources, right? Otherwise, we compare apple to oranges. So queries, relatively simple. We use some embedded mechanism like BERT in our case. We use BERT, run it through some BERT pre-trained model. We get an embedded vector. You have to use the same black box, and you do apply the same for resource. But how you do it for the resource? In the resource, you assume that you have a sample documents. So here we benefit from the previous work that I just mentioned. This is why I gave that refresher of the literature. So we use the sample documents from each of the resource. We run each of them through the encoder. Then we use some sort of pooling. In our case, we use mean pooling. In the paper, if you go, we analyze a few others like max pooling and others. This one turns out to be the best. And we use the mean pool representation to represent our representation of the resource in the embedded space. So that those 2 vectors are the input vectors in our GNN. So this is the next step, constructing the graph on which we train. The graph has 2 types of nodes, the query nodes from the training data and the resources themselves. Then we have edges. We have 2 types of edges. The first in yellow are from the query to the resource. Those are relative to the relevance that we can compute, because remember we had this local index, right? We can issue the query, you can compute the relevance. So those are weighted edges. And then between resources, we can use the vector that we computed in the previous slide, and we can use the cosine as a measure of their similarity. Of course, we can use whatever other metric or formula between vectors that is suitable, but cosine tends to be quite good and quite stable when we have in the embedded space, right? You compare vectors because you look at the angle, right? So magnitude doesn't play as much of a role. So once you have the GNN constructed, right, the graph constructed, we have the initial embedded vectors for the query and the resource. The next step is the training part, right? We only, in this case, let me first say, we only use 2 layers. it's pretty standard. We rarely go to 3 or more with the graph neural networks. Two other things that I have to mention here. We use a graph convolutional network for this kind of, for our purposes. And it also has to be relational. Why is that? And perhaps this will take us to the formula on the right-hand side. It's a bit busy, but the main takeaway from there, you see that E over there, that means that you do the aggregation or the updates of the embedded vectors relative to the type of edge. Remember, we have two types of edges, the relevance between the query and the resource and between the resources themselves, right? So you do not mix them up. You have to do it per type of relation. So that is applied with each layer, right? And we take the input embedded vectors and we update them. And at the end, our goal is to optimize the training function that the similarity observed for that we computed cosine over the vector of the query and the resource is close for those resources where the query can be answered with higher relevancy, and further away for those resources where they are not relevant to the query. So this puts together the entire framework of the proposed solution. We call it Fed GNN, federated, that Fed stays from federated. The top part is, it's what I described so far is the training part. So I'm not going to go over it. What is important there is that once we finish the training, we create a resource embedding store. We store all the embeddings relative to the resources, right? That's important for us. So now let's look at what happens online after we computed all these embeddings. And we have also the general network computed. We get a new query, right? The same thing happens. We take the query. We don't have an embedded representation for it. We have to take it through the same, whatever embedding tool you use. In our case, again, use the BERT encoder. Get for the new query and embedding the same space, right? They have to stay in the same space. Otherwise, it doesn't make sense. And then you create a graph again, right? So the graph now is between, you run that query against your, you compare your embedded vector for the query with those of the resources. You get all of them, those relevant scores, right? Then you run that's your graph now, right? Then we have the graph neural networks computed from the training part. We run that through our GNN model, and that will update the embedded scores for our resources. And then we use that, the updated embedded vectors, to compare with the embedded vectors of the query, which will also be updated through this GNN. We do cosine over them, we sort, and that will be the ranking. Okay. So going back to the example, the earlier example, now because we please note those edges, right? So initially, if we didn't have any relationship between the sources, neural net will not be able to give some of its relevance to the other sources. And now with GNN, because we can intuitively accept that there is a connection between neural nets and deep learning, and there is a connection between deep learning and machine learning, but there is not a major or intuitively we can observe there is not much of a connection between R3 and R5, right? So that signal will not propagate all the way there. So now those R1 and R2, which previously were not treated as serious contenders to return relevant documents, now become serious contenders because they retrieve some of the signal from R3. Questions? So experiment-wise, in all of these tables, I'll talk about this perhaps at the end. I'll mention something funky about the state of literature. So why we need so many tables. At any rate, so you observe that to use ClueWeb Online for the two of them. One has 123 sources. And in that, we have the measure here, T. That T stands for how many resources you eventually keep out of 123, right? And you submit the queries there. And the way so for this one here, for the first one, you observe that we outperformed in the state of the art. The same when you move to this other one, which should be the same, but as I said, I'll mention why that is why we have to go through this awkward evaluation. Let me put it this way, let me tell you about that right now. The space suffers from not having a uniform benchmark. That's the problem. So some papers before ours, they use that. This other paper uses that. And the reviewer say, why did you compare with that? So eventually you have to please everybody. You have these awkward things. Okay. So that's the reason. Again, don't tell the community that I said that. So then this other data set, FedWeb 14 is also a recognized benchmark in the community. So you have to compare against that as well. That other one, the baseline use NTCG rather than the precision of 10 or precision they use also precision of 5. So you have to use the same thing. So we have a consistent comparison with the state of the art. And you observe again that we are able to outperform the state of the art with adding this GNN representation. Okay, so the contribution in this, we believe that this is one of the first work that adds neural network to the distributed information retrieval, which kind of lagged the research between like about 10 years, was pretty much dormant. So we believe that this is the first work that kind of resurfaced the interest in this work. And it shows that we are able to achieve meaningful performance increase, right? In some cases up to 42%, depending on the data set, depending on how you look at it. As I said, the fact that we don't have and that perhaps we should motivate the community to build a benchmark. I know we talk about benchmark being a sort of a boring task, but somebody has to do it, right? So in this community, I challenge the community that we need such a benchmark eventually to construct. Oh, sorry. Yes, please. Yeah.
So I have two questions. My first question is that if I understand correctly, in order to get a representation for each resource as you use basically.
Alireza, could you speak a little louder?
Yes. So basically, based on what I understand, if I understand correctly, in order to get a representation for each resource, you use basically you use an off-the-shelf encoder. Feed every document to that encoder, you get a bunch of representations, and then the mean representation of that would be the representation of the resource.
Mm-hmm.
My question is, how large are the resources?
The resources themselves?
Yes.
Thousands of documents.
Thousands of documents. So then the other question is like, it's very interesting that just simply getting an average of representations of all the different documents that can be in one resource can give a good representation for that document. So I was wondering, did you, for example, try other methods, maybe, I don't know, keeping multiple vectors for the resource or something like this?
So that's a good transition to the next one, where I talk about the boxes as perhaps a better representation for, yeah, that's a great insight, yes.
I have a second question too. So one other way to solve this problem would be through rank fusion, right? Did you, for example, because you have multiple resources, you can use the same query, you get this from different things, and then basically fuse those different rank lists into the one single rank list. I was wondering, have you looked at that problem?
So yeah, the answer is two parts. I look at that, I'm familiar with that. the problem that I presented so far, it's a step before that. So meaning I cannot afford, so imagine I have, perhaps I wasn't explicit, perhaps I have, say, 200 data sources, search engines, mini search engines, right? So my goal is to not to submit the query to all of them. That's the trivial way. I'll submit. Then everybody sends to me, I don't know, 100 documents each. Then I have to do the fusion between them and then come up with the top, whatever. So I want to avoid that. So the problem here is rather than send the query to all 200, I send to 4. The 4 that are likely to send, to give me once I get the documents, that will be, those 4 will be enough for me to return the relevant documents that the user needs. And then I do the fusion. Yeah, that's a step later in the process.
Thank you.
Yes.
I noticed that the results of the experiments were mainly using precision-based metrics. And
Yes.
I guess one thing that I'm wondering is, when you are sending your query to multiple different collections, wouldn't that mainly benefit the recall? Because even with one of those collections, you might be able to get perfect precision. But something that it definitely adds is the recall as you're retrieving more relevant documents. So why aren't there like...
I have a pragmatic answer to that, and then a science. Pragmatic, because you have to evaluate against state of the art. Nobody does it, you don't do it, right? So if you introduce a new metric, why did you? Because in this case, you have to first evaluate yourself against the competition, right? So if the competition didn't use that metric, why would I introduce it, right? So that's the first. Second, if I introduce it, then we have to talk about analytically what insights that brings. And that's a very, very good question. If I want to see, oh, did I miss any relevant answer? Because the recall is pretty much what it says, right? It's there is a document out there that the user wanted, but I didn't retrieve it, right? So that's a great question, and I guess relates to your work. It's good that I saw your work before that total recall. Yes.
One part I missed. So how you got the query resource relationships?
So after you get the embedding, you can use the cosine.
Oh, so you use the cosine similarities of the embeddings.
Yes. Yeah. You can use that, or as I said, there are multiple. You can
Because
use
I
that,
was
or
thinking,
we can use if you build that local index, you can use whatever mini search engine you use locally to get to the initial relevance.
because I was thinking maybe a better way, just more difficult to make it work in practice, will be you have a large enough collection of queries that can cover most of the corpus, or at least all the topics in the corpus. And then you can have a method to evaluate the quality of the retrieved results for each query. Then you can build a relationship based on the query performance, basically, of each collection.
So
then it will be more like query
s-
performance focused relationship,
right.
not like.
So I see what you're saying. Sorry to interrupt you, but one, in the past, I wasn't clear about it. I'm not sure what I said. One strong assumption that we make is that these collections are uncooperative, meaning that I really don't know what they have fully.
Okay.
I use the sample to
Okay.
discover what they have. So in your case, I need some cooperation from the resources, right? But at least in this case, and at least in the traditional way of solving the problem, we assume that the resources are not cooperative. Yes, please.
Did you explore how sensitive the performance is to the graph topology?
No, that's a great question. No, we should have. Yes.
Because you build the graph off the initial embeddings, which are just off-the-shelf pooling from BERT. You could have like a fully connected graph or a sparsely connected graph.
The full, I don't think it matters as much because you get the connected components and you can do distributed training on each of them. But there are, the density of the connections, maybe one is like a star connects to everybody, but one is off as one or two. It shouldn't matter so much, but there is something, there is something to be said about that. And we didn't do it. That's a great question. Other questions? Thank you. So now we move to this other topic that was alluded by Alireza, that is a vector good enough to give me a good, like we did the average pooling, right? So that was, but as you noticed intuitively, we average, you may have a document that talks about one topic, this is about other topic, this is other topics. So a collection has multiple types of documents. So when you do the average, we kind of diminish in very important, right? So we said, can we come up with a better representation for the resources? So we said, how about boxes, right? And the problem remains the same, but now we want to model the resources themselves as boxes, and we plug them again into our pipeline. And I'm meant to describe this concept. Okay. Yeah, so how should I? Is it better? So that overlaps with the. Okay. So this is the overall framework for resource to box. We follow the more or less the same pattern that we had before. We try to get an embedding representation for the query and the resource itself. And for each resource, we use a sample of the document. However, in this case, in this newer methodology, a box, you have to define a box. And I'm going to give a bit more formal representation of the box. But in a hyperdimensional, in a higher, in a d-dimensional space, we have hyperboxes, right? Hyperrectangle in our case. You need at least two vectors to represent the box. In our case, we have used some sort of a center of the box. And then we have this other vector, it's called offset, that will tell us in each dimension how much it extends, right? If it's a 3-dimension, you have this way goes, I don't know, so many units, Y so many units, X so many units, and so on and so forth. So that's the offset vector. So these two vectors, we have to learn, okay, to infer for each box how far it. So pretty much what you want is to assume, let me give you the intuition, perhaps this is better here. So what we want is these boxes, we assume that each of these sources are together in a giant semantic space, together, right? So the box, the intuition of the box is, what is this coverage in this space that you as a resource assume, right? Of course, an estimated one, right? We use the documents to estimate that. And initially, and then we use we use the same, as you see, observe here, and I'm going to talk about the GNN again to refine the box. But the refinement is more to say how far you, because there are these other neighbors you have that they tell you also their information. So they can say you encroach too much in me, push back, right? Or you went too far. You don't really represent us because I know better, right? I actually have this. So you can think like a tag game where the resources now in GNN, they will tell each other how to shape the box, right? So I actually, when the student came up with this diagram, I loved it a lot. It gave a good intuition about what we tried to achieve. Because if you think about in the space of embeddings, and particularly documents for a resource, if you have each of these dots here represent the document themselves, right? And the color represent the topics, right? So we can have articles from Nature, from Microsoft Academic, and so on and so forth. We can, and in the previous method, which one of you mentioned, when we do the average, we collapse them in one dot. These giant dots here on the second plot. But you can see that you can lose a lot of information about the resource itself. So when you go to the box, that it's a better representation, and also the overlap between them, because these boxes mean that when you have an overlap, means that these resources overlap in their coverage. Okay. So the definition of the box, as I said, I promise I'll give the definition, is nothing fancy. So I want to mention there are a few ways to define a box in a hyperdimensional space. This is one of them, where you give the center, in this case, O, or C. Okay, think of this as the centroid, but it's not really a center, but this the box, and from there, it tells you how far you can go in each direction. That's the offset. And every point that is inside the box, right, is bounded by the boundaries that you can easily compute given the center and the offset. Why is that relevant? Because when you have a query, and we'll talk about that shortly, particularly if you have a boxes, it's geometrically speaking, it's quite easy to determine whether a query, when we are in the embedded space, of course, is inside the box, outside the box. The formula it's a easy computation. Okay, if you use other representation form rather than box, it's not as easy. So the learning has two steps. The first step is very similar to what we did before. We aggregate the features from the documents from each source, right? We did that before, right? What we do next is a bit different. We want to refine the embedded representation of the boxes of those two vectors. So one thing that I should mention, in the previous presentation, the one with the straightforward GNN, we only updated one vector, right? Now we have two vectors. Those two vectors, each node will have two vectors that have to be updated. It's not just one, two. So that's what happens in the second step here. And finally, what we'll get, these two vectors, which is a refinement after you start from the original embeddings, will give us the final representation of the boxes, which represent individual resources. So, so we have about 10 more minutes, perhaps. So this is pretty much going in details of the okay. Yes. So so if you remember the original diagram, what I'm going to go talk about now is the individual steps over there, right? So why attentive pooling is because we now want to make sure that the query and its relevance play a role when we look at the documents. So a document that is highly relevant, I want to give it more attention, right? And account for it more, assign a higher weight than the others. You observe that we have about the same formula. This is a classic formula in the with the GNN, but we observe that we have different weights for the center and for the offset. Center, you can think of it as more or less like finding the centroid, right? It's a classic. Offset uses the same documents, but with a different learnable weights, right? Because that needs to tell us how far in each direction we have to go. This is, as I said, I mentioned earlier, I think already, that when it goes to the GNN now, we don't update one vector, we update two per node. And the same thing here, when I look in the neighborhood of a node, and I look at these nodes, and now I'm also using sort of an attention that omega to kind of say this neighbor of mine is actually more similar than this other neighbor. I want to assign more weight. That's what this omega does when I update. And the other one here is a normalizing. So why do that? Because this relates to your question, the topology. We may have a case when a node has many neighbors, when another has fewer neighbors. So this is a classic way to normalize in GNN to account for that, this square root of what you observe. Now, I mentioned this already, but perhaps it's worth mentioning because we changed a bit the space, not the formalism, the abstraction. Now we have boxes and vectors. Our queries are vectors and our resources are boxes. Now, how do you judge relevance? right? Because you have to come up with a different, because sign doesn't work anymore. So now we have to think a bit geometrically about this. So what we do, use projection in the higher dimensional space, and we look at the projection. The projection is outside the box, not so good. If you fall inside the box, perfect. But the question is, can we use both? Because even if you fall outside the box, perhaps how far you fall is also an important hint. Okay, you may, because remember, the box is an approximation of, so it may be that the actual if we have all the domains, that box perhaps extends a bit further. So you look at that distance as sort of a as a guide, right? The further it is, clearly that the resource is not relevant to the query, but it is close enough. This way, we compute both the inside and the outside. The outside plays another interesting role, because then once it is inside, we also want to know how far it is from the center, from the centroid. Okay, so and then we compose it with this linear expression where that parameter here is a hyperparameter, and it has to be either manually set or empirically or learned. Yeah. So eventually, this is the learning function for the new approach. Is a marginal ranking loss, and we add this lambda to account for the fact that we actually don't know. Really, the box is an approximation of what the resource is, right? So is this so that when you fall outside, I'll give you a leeway, right? Think of it like if you close your eyes and imagine there is the sample box, and there is this other hollow box that it actually represents the entire resource. That's lambda is kind of that leeway to account for it. That's another hyperparameter in the process. Yeah. So with this representation for the resources, again, we went to do the evaluation, used the same data sets. Again, we look at precision at 10 and DCG at various points, 30 and yeah, for 10. Oh, maybe it's a different plot. And you observe again pretty good stable improvement across the board. Right? This is our, and we compare also against our own algorithm, which is the second from the bottom. So improve on that and improve on everybody else. And we repeat these experiments multiple times to see whether the improvement is statistically significant. So those pluses are for that reason there. Yeah, so a few other analyses on that. The same idea as before. We had to do this because we don't have a benchmark. When you look at these papers in the literature, they use pick and choose which data set makes them look better. And I didn't say that. And they use that. And when we had to write the paper, the reviewer said, how about that? So we had to do that to please them. This way, we have this sort of ununiform way to compare. Okay. So again, the takeaway here is that really the box is I believe, and we believe, is the right approach to represent a resource, because the vector alone doesn't do justice to the diversity of topics that the resource stores, right? So that finishes the neural part. I have a few more minutes. If I can take 2 more minutes, James. And I'm going to present a newer work that we just got accepted related to intention of using, so this is unrelated. So think of it like take a break. It's like telling LLM, forget about what we talked so far. We start a new prompt. Okay? So I'm doing the same here. So, but this is still in the information retrieval. So this is my student Fan Ping. She just got her paper accepted a few weeks ago in the website. But this is related to intention of why people share URLs to external documents in social media. And so this is for me at least, is a fascinating problem. Why would I insert a? And we notice many reasons. So, for instance, in the top part, you may feel that that's an advertisement. Actually, the person is asking for advice. Hey, have you used this product? Can you say this? It's not the first time you see it, may feel that it's an advertisement. In this other one, which was really interesting, we found many such examples. This is from my former student Abdullah, and he found many of them where people use sports events, right? You are looking, hey, I want to see this guy, I want to this game, but I don't have access to it. And these people only use that to clickbait you. Because actually this link doesn't take you to the game, it takes you to something else. Okay? And you may have to even share some information that you should not. Anyway, so the intention, if you are able to detect that intention, you can perhaps create even defensive tools that against these attacks. But anyway, what she did for this paper, she was looking at, she developed an detection taxonomy, has multiple layers. I think the top layer is 6, and then a few others, quite a few others below. And then she used it to show that it can improve micro-block retrieval. How many of you are familiar with that topic? It used to be a big topic, or a hot topic. I don't know if there is a track data set for it, by the way. So I'm not making up this kind of task. If you go to track, there used to be a competition on this. So she used this to show that the intent has a downstream benefit. So in this case, she used this retrieval. So for instance, you have the query TORP return into 2012 Olympics. Assume that you have, these are the, say, the tweets here, right? We call them, she used the blog because the competition or the coin name in the community is micro-block retriever, micro-block retriever, sorry. So if you do plain retrieval with the state-of-the-art tools, this is kind of what you get, right? These are on this track data set, so use the long-form track. But if you add to it the intention, you may discover that some of these tweets that are part of the top K should not be there. Because for instance, that one over there, entertainment, is not relevant. The user actually is looking for information, is looking to learn something about that. But this system did build a few years back, were not using intention and were not aware about how to prune or clean the topic. Anyway, so I'm stopping here. I would like to acknowledge the people who work with me on the neural network, neural approaches for distributed information retrieval. And thank you for your attention, and thank you for having me here. I really had a great time.
I think we can probably swing one or maybe two questions if people have them. So Alireza.
Thank you. I really enjoyed your talk, and also specifically about that resource toolbox. Just I have one question. Why you made this assumption that you have the center of the box and then you move from the center to the both side, basically the same?
No, it's not the same.
Oh, it's not?
No, because the vector is multiple entries. Each the
yes,
offset,
but the offset is the same offset, and if it's the center, then
the offset.
right?
You can just move the center so it's equidistant from both
What
sides.
is that?
Right there.
So the offset, right, has as many entries. So there are 4, right? 4 entries. No, that's 4 dimensions. In the first dimension, I can go 2. In the third dimension, I can go 5. Third dimension, I can go 7. Or the other one 0.
Yes, that's right. But for example, for each specific dimension, you go, for example, you go this specific number +2 and -2, right?
Yes.
But if we have 3 vectors or 2 offsets for each of them, we can, for example, go this amount away from the center, from the left, and also a different amount on the
Oh,
right,
I see
right?
what you're saying. Left, yeah, I see what you're saying.
Yes.
Okay. Yeah, that's a good point. But yes, right now I don't do that. It's in the same, yeah, from left to right, it's the same unit, but
Right.
it's different per dimension.
But what if you, instead of having the center, you get there basically a max pooling? Then the single offset would resolve that problem, right? Because from each dimension you have the max, and then the offset would. I was just wondering if you tried, for example, something beyond just min pooling for.
Oh, yeah, we did. I removed this actually.
Yeah.
We did. Let me see. I removed it today in the morning when I, so here, this is the slide. Let me show it. It's an ablation study. And over there, you can see there is a mean, max, pulling, and all of that.
And min was the best.
Mean still, this one, the one that I kept is the one that performed the best. Yes. So,
Thank
you know, when you present, you pick and choose what to cover. Yes, go ahead.
So a lot of the motivation you gave for why you represent resources as boxes, I think also could apply to queries. So is there a way you didn't represent, I see you're smiling, is there a reason you didn't represent?
Works for that. Yeah, we look back who graduated, has finished pretty much, but he graduated and we had this conversation, you are all students here, you graduate and you leave us, you work unfinished. So I'm looking for another student to finish that. But we look back who had pretty much done most of the work, he pretty much done it. So yeah, here's one query to box, where the query becomes a box itself. And then you have to change the mechanism, the formula by which you compare query to the box, right? It's a query, it's a box overlay.
Yeah.
Yeah. So yes, thank you. That's a great point. Yeah.
Cool.
Yes.
I have a
Okay,
question.
this will be the
about-
last question. Okay.
I have a question about the motivation of the distributed retrieval.
Yes.
Is it usually the case that you have just multiple collections and you want to do retrieval over all of them? Or is it sometimes also the case that you have a very large collection and you deliberately break it down into multiple resources to just distribute the load? Like, is that?
Both, I guess, but the main one is the previous one, what you said, that you assume that there are many collections out there that are uncooperative, right? Twitter doesn't collaborate with, my understanding, with Google, right? Or LinkedIn, if they would allow you to search. So this is one thing that we are, myself and a colleague of mine who moved now to Riverside, we want to do this integrated search over scientific literature and how it is discussed in social media. So for that, there is no other way to look across multiple data collections. LinkedIn, Twitter, Reddit. Now with the open review, you have the paper itself, the comments, and so on and so forth. And I don't think there is one engine that indexes all of them.
Okay. Let's thank our speaker one more time. Thank you so much. Those of you who are local, opportunity to mix and talk to Eduard is for at least 25 more minutes. But I think I'll shut the Zoom down. Thank you for the remote folks. Still two of them online. But,